Okay, so here we are. We are now in chapter 8. And chapter 8 is about applications of integration. And we're going to start with section 8.1, which is about arc length. So 8.1 arc length. Here's the idea. Suppose you have a curve and it's defined between x equals a. So it's y equals f of x, and it's defined for x between a and b. And suppose we subdivide into subintervals of size delta x. So delta x is b minus a over n. And so a is x0, and then you have x1, and so on. The width of the subinterval is delta x, etc. So suppose we go to the kth subinterval, between xk and xk plus 1. And let's look at the way we're going to compute arc length is we're going to connect the dots on the curve that are above the subdivision point. So you get these straight lines, and that's going to approximate the arc length. So let's blow up the kth subinterval, what's going on over there. So here's your curve. Here's the point. Here's xk below this point. Here's xk plus 1. And we're connecting the dots to make a straight line segment. And I want to compute, I'm going to estimate the length of the curve by computing the length of the straight line segment. So how does that work? Well, this point here is xk, comma, f of xk. And this point here is xk plus 1, f of xk plus 1. So let's call this distance here L, and I want to compute L, this straight line distance. So how do I do that? I form a right triangle. Now the base of the right triangle is the difference between xk plus 1 and xk. In other words, delta x, and the height is delta y. So L squared, or L, is the square root of delta x squared plus delta y squared. And that's an approximation to the length of the curve between those two subdivision points on the curve. So if we're going to integrate, we're going to sum up over all subintervals and then take a limit as delta x goes to 0, and then we get the formula for arc length. It's L. It's the integral from a to b. So that means we've summed up and take the limit as delta x goes to 0, and then we get the square root. Oh, okay, so I want to rewrite this square root. So we can rewrite, let me do that over here on the top of the screen. So the square root of delta x squared plus delta y squared, I can factor out a delta x squared through the square root, and that's going to give me a delta x on the outside. And what's left over is a 1 from the delta x squared, and then a delta y over delta x quantity squared. So now in the limit, that becomes 1 plus dy dx quantity squared times dx. So that's the formula for arc length. Now, the nature of arc length is typically hard to compute because of this pain in the next square root. So a lot of examples you won't be able to compute. So the book specifically gives you examples that can be computed. So I'm just going to do a few examples. So let's try the arc length. Let me first of all put back the arc length function, the arc length formula. So it's the integral from a to b of the square root of 1 plus dy over dx quantity squared times dx. Okay, so now let's do an example. Let's consider the curve y equals 2/3 x to the 3/2, where x is going from 0 to 1. So what is arc length? What is the arc length formula? Well, first of all, what is dy dx? Dy dx is 2/3 times 3/2 times x to the 1/2, so it's x to the 1/2 power. So the length of the curve, and this is between 0 and 1, so x is going from 0 to 1, the curve looks something like this between 0 and 1. So we're going to get the integral from 0 to 1, the square root of 1, plus the derivative squared. The derivative is x to the 1/2, so x to the 1/2 squared is x times dx. So now we have to integrate this function. So I'm going to do a u substitution. U equals 1 plus x du is then dx. And then what are the limits of integration in the u variable? Well, when x is 0, u is 1. And when x is 1, u is 2. And then you're going to get the square root of u, which I'll write as u to the 1/2 du. Okay, and the antiderivative of u to the half is 2/3 u to the 3/2, evaluated from 1 to 2. So you're going to get 2/3 times 2 to the 3/2 minus 1. And that's the answer. Okay, so that is our first example. Okay, so uh, I neglected to save the first slide, I just noticed. It's not a big deal because I wrote the formula down on the second slide. Okay, so here is a remark. Suppose the curve is not given by y equals f of x. Suppose it's given by x equals g of y. So x equals g of y, where y is going from c to d, let's say, is a curve. Well, the arc length formula is given in the same way. You integrate from c to d now, the square root of 1 plus the derivative dx dy rather than dy dx squared times dy. So for example, we can look at the curve y squared equals x, which is a parabola from x from y going from 0 to 1. So that's actually a parabola. It looks like this, but y is going from 0 to 1, so it's this portion of the parabola. And we want to compute the arc length. So what is dx dy? It's 2y, so the length is going to be given by the integral from 0 to 1, because y is going from 0 to 1, of the square root of 1 plus 2y quantity squared times dy. So in other words, so now we have to integrate that function. So let me save the slide and clear the screen so we can actually do that integration. Okay, so it's the integral of the square root of 1 plus 2y squared dy from 0 to 1. Okay, so let's first of all do the indefinite integral. So we can this should be a trig substitution. 2y should be tangent of theta. Okay, so 2 dy is secant squared theta d theta. And dy equals 1/2 secant squared theta d theta. Okay, so let's worry about the limits of integration in a second. Let's just set up the integration. So, all right, so we got the square root of 1 plus 2y quantity squared, which is the square root of 1 plus the square of the tangent. So that's the square root of the secant squared, or the secant of theta, times dy, which is 1/2 secant squared theta d theta. Now we have to figure out the limits of integration. And you're going to see there's going to be a little bit of a problem with that. Okay, so let me draw a right triangle, put theta here. So tangent theta is opposite over adjacent, so it's 2y over 1. Okay, so I had to make a pause there. So the hypotenuse of this right triangle is 1 plus the square root of 1 plus 4y squared. Okay, the limits of integration can be computed as follows. It's going to be tricky though. Let's see. So y is 1/2 tangent theta. So when y is 0, uh, 1/2 tangent theta is 0, or tangent theta is 0. And therefore, if tangent theta is 0, theta should have been 0, right? Now, what about when y is 1? When y is 1, then the tangent of theta will be 2. So we want theta to be the inverse tangent of 2. So theta should be the inverse tangent of 2. So that we could put it in a calculator and get an estimate, but let's just rename this angle alpha. Okay, so therefore the upper limit of integration is alpha. We'll see that alpha is going to go away. Okay, so what do we got? So we got 1/2 the integral from 0 to alpha of secant cubed of theta d theta. Now we computed the integral of secant cubed, and we got the following. This goes back to chapter 7. This is going to be 1/2 secant theta tangent theta plus 1/2 ln secant theta plus tangent theta absolute value. And we're going to evaluate this from 0 to alpha. So what do you get? Well, if you factor out the so if you let's factor out the 1/2 with the halves to get a quarter. Now we stick in alpha. We get secant alpha tangent alpha plus ln absolute value secant alpha plus tangent of alpha. And then if we plug in 0, we're going to get 0. So that's not going to do anything. Okay, so now we have to figure out what secant of alpha is. Okay, so so what is secant of alpha? What's tangent of alpha? We know that tangent of theta is 2. So let me redraw the triangle here. So okay, so we have alpha. Alpha tangent of alpha is 2, so 2 over 1. And this is the square root of 1 squared plus 2 squared, or the square root of 5. So we get the secant of alpha is hypotenuse over adjacent, so that's the square root of 5. We get the tangent of alpha, which is 2, plus ln of the square root of 5, plus the tangent of alpha, which is 2. So this can be re-expressed as the square root of 5 over 2 if I distribute the 1/4 plus 1/4 ln of, say, let's write it like this, 2 plus the square root of 5. So that is the arc length in this case. Okay, so the last part of this of this section is to consider arc length as a function. Let me explain what I mean here. Suppose I have a curve that's defined starting with t equals a, with x equals a. So you got y equals f of x, and x is greater than or equal to a, let's say. And then we have some number t that's larger than or equal to a. So then what we can do is we can find the arc length of the curve from a to t of the square root of 1 plus dy dx quantity squared dx. So let's call that function s of t. So what is this function doing? Well, from a to t, you're taking the length of the curve between a and t. So it looks like this. It looks like this. You're taking the length from a to t. And as t increases, the length gets bigger. So this is actually this curve is actually this function is increasing, in fact. Okay, so now I want to point out that if we take the derivative of s of t, we get s prime of t. By the fundamental theorem of calculus, what this is the square root of 1 plus dy dt squared. So the derivative is the integrand. That's what the fundamental theorem of calculus says. Okay, so I'm going to do an example of the arc length function, but I need some space to do it. So let me clear the screen. Okay, the example goes like this. So find the arc length function of y equals x to the power of 3/2, starting at x equals 1. Okay, so what is that going to be? So s of t is the integral from 1 to t of the square root of 1. Now, what is dy dx? Dy dx is 3/2 x to the 1/2. So it's 1 plus 3/2 x to the 1/2 quantity squared dx. Okay, so in other words, it's the same thing as the integral from 1 to t of the square root of 1 plus 9/4 x dx. Okay, so we're going to do this by substitution. U equal 1 plus 9/4 x. So du is 9/4 dx. In other words, 4/9 du is equal to dx. Okay, if we do that, then we have to also figure out the limits of integration. So when x is 1, u is 1 plus 9/4. So it's going to be, what is that? That's going to be 4/4 plus 9/4 is 13/4. And when x is t, u is 1 plus 9/4 t. And it's going to be the square root of u du times 4/9 du. Okay, so what do you get? You get 4/9 times the antiderivative of u to the 1/2. That's 2/3 u to the 3/2 evaluated from 13/4 to 1 plus 9/4 t. So what do you get? You get 8/27. That's I multiplied the two constants together. And then it's 1 plus 9/4 t. There should be a 3/2 here. So to the 3/2 minus 13/4 to the 3/2. I think I'm going to leave it like that. So that's what S of t is. S of t looks like this function here. It's not completely simplified, but it's good enough. Okay, so there you go. That's the arc length function. That's arc length. The next topic is surface area.